In this entire chapter, we're studying the simple constant coefficient linear homogeneous differential equation system dy equals ay, where a is a matrix. Usually most of our examples will be 2 by 2, and y will be a 2 vector of 2 components. X and y are functions of t. And in section 1, we learned that if you can somehow come up with 2 independent solutions that aren't just multiples of each other, and then the general solution will be a constant times the first one plus constant times the second one, linear combination of those two. And once you have the general solution, you can choose the constants so that they satisfy whatever the initial conditions are. So we don't just want one solution. We're not through. We need the general solution so we can satisfy initial conditions. But there was no clue as to where they got these solutions from. They just gave them to us, and you plugged them in to verify that they were solutions. And once you found 2 independent solutions, you could find the general solution and the one that satisfies particular initial conditions. Well, you may have noticed that all of the solutions they gave us were of the form e to the lambda t, where lambda is a constant. So let's try solutions of that form. So we're going to see that the solutions are related to the eigenvalues and eigenvectors of the matrix A. So let's review chapter 4, and matrix algebra is all about the eigenvalue problem, but most of you haven't had that, so we need to review a little bit here. You may need to read this part more carefully if you don't remember what eigenvalues and eigenvectors are. But what are eigenvalues? They're eigenvector is a non-zero vector such that a times that vector is just a scalar multiple of that. So if you multiply an eigenvector by matrix A, you just get a scalar multiple of it, and the scalar multiple is called eigenvalue, and the vector, the non-zero vector, has to be non-zero, because if v is allowed to be 0, a times 0 is lambda times 0 for any lambda. So, but a non-zero vector, lambda, if a times some vector is lambda times v, then v is called an eigenvector, non-zero eigenvector. Lambda is eigenvalue. And you may remember how to find eigenvalues and eigenvectors. We'll come back to that, but the key thing is that AV equals lambda v, where v is a vector, A is the matrix. Okay, so we're finally going to find out where these solutions came from in section 1. A solution of this problem will be e to the lambda t times v, where v is an eigenvector and lambda is an eigenvalue, and that's what we're going to show here. So if you can find an eigenvector and eigenvalue, eigenvector v, non-zero vector, and eigenvalue lambda, then we're going to show that e to the lambda t, the scalar e to the lambda t times the vector v, where v is the vector xy, those are constants, is a solution. And just plug it in, and you plug in your alleged solution on the left-hand side, and the derivative of e to the lambda tx, e to the lambda ty, you just get a multiple of lambda in both. You can factor out the lambda, and what you have left is just your original y. On the other hand, the right-hand side, a times y, if y is e to the lambda tv, the e to the lambda t comes out, it's a scalar. Av is lambda v, because v is an eigenvector, lambda is the eigenvalue, and e to the lambda t times v is y, so that's just lambda y, so their two are equal. So in other words, we just simply plugged in e to the lambda t times v, this here, e to the lambda t times v, where v is eigenvector, lambda is an eigenvalue. Plug that into both sides, they're equal. That proves that it's a solution. Well, normally for a 2 by 2 matrix A, you'll normally have 2 distinct eigenvalues, so that gives you the 2 solutions you need. If lambda 1 is an eigenvalue with its eigenvector v1, lambda 2 is the other eigenvalue with its vector e2, there's your 2 independent solutions, and the general solution is linear combinations of that, and that's exactly what you need, is 2 independent solutions. So you have the general solution if you can find the 2 eigenvalues and the corresponding eigenvectors. Well, how do you find the eigenvalues and the eigenvectors? Well, we spend a whole chapter talking about that in matrix algebra, but in case you don't remember that or you haven't taken matrix algebra, more likely, you're trying to find a vector, an eigenvector xy, and an eigenvalue scalar lambda such that A times the eigenvector is lambda times the eigenvector. You write this out, take everything on one side, and you have a linear system for x and y equal to 0, 0. And if this matrix has an inverse, you can just multiply by that inverse and you'll get, inverse times 0, 0. Any matrix times 0, 0 is 0, 0. So you'll get x equals 0, y equals 0, which is not legal. X and y can't both be 0 because eigenvector has to be non-zero. So the only way you can have a solution to this, other than the trivial solution x equals 0, y equals 0, is if this doesn't have an inverse, which means that this matrix has a 0 determinant, so it has no inverse. So you take the determinant of this matrix, set it equals 0, you get a quadratic equation for lambda. When you set the determinant equal to 0, get a quadratic polynomial, and you either factor it or use the quadratic formula to find the roots, and usually there'll be two distinct roots. In this section we're going to assume they're real roots. They can be complex. That'll have to deal with that in section 4, but for the moment we'll only take examples where the roots are real, and usually there'll be two distinct roots unless the discriminant is 0, in which case there's only one root, and that's section 5. We're not actually going to skip that. That usually won't happen. So we'll assume that there's two distinct roots, lambda 1 and lambda 2. Now how do you find the eigenvectors corresponding to those? So to find the eigenvalues, basically you subtract lambda from the diagonal, set the determinant equals 0. You'll get a second degree quadratic polynomial, find the roots of that. And then how do you find the corresponding eigenvector? Well, you go back and remember the eigenvector satisfies this or this. So once you found the two values of lambda for which they're non-zero solutions, you plug in your first value of lambda and actually solve for x and y. Then you plug in your other value of lambda and actually solve for x and y. And there will be non-zero solutions because the determinant of this system is 0, but any multiple of the solution, eigenvector is not unique. You take any eigenvector, you multiply it by a non-zero constant, it's still an eigenvector. But so this is the system here. You set the determinant equals 0 and find the two values of lambda, go back for each value of lambda, plug it in here and solve for x and y, and that's your eigenvector. And once you have your eigenvector and your eigenvalue, the solution, they call it a straight line solution, we'll see why, is e to the lambda t times the vector xy, the eigenvector. So eigenvector, eigenvalue, you get the solution, one solution. Other eigenvalue, corresponding eigenvector, that's other solution. General solutions, linear combination of those. So for example, suppose the matrix is this. You subtract lambda from the diagonal, set the determinant equals 0, solve for lambda, and we found that the eigenvalues are 4 and 1. And for 4, what's the eigenvector? Well, you subtract 4 from the diagonal and set that equals 0 and solve for x and y. For the other eigenvalue, subtract 1 from the diagonal, that times xy equals 0, 0, solve for x and y, that gives you the other eigenvector. So you have one eigenvalue, its eigenvector, any multiple of it is still an eigenvector. Other eigenvalue, so one eigenvalue is 4, and eigenvector is 1, 1. The other eigenvalue is 1, eigenvector is minus 2, 1. So your general solution is any linear combination of those two independent solutions. And now you can apply your initial condition. Whatever it is, you set t equals to 0 and set this whole thing equal to the initial condition vector and solve for k1 and k2. So the homework problems are all just like the example. You find the eigenvalues, subtract lambda from the diagonal, set the determinant equals 0, solve, find two eigenvalues. There'll be two real eigenvalues in these problems, in this section at least. Later they'll be complex and that's more difficult, but won't happen in this section. And then you go back and find the corresponding eigenvector, and then the solution is e to the lambda 1t times first eigenvector, and the other solution is e to the lambda 2t times its eigenvector, and the general solution is a linear combination of those. Then, well, let's see, these, they don't give you initial conditions, so you just write the general solution as an arbitrary linear combination of the two eigenvector pairs, but the later problem, they do give you initial conditions, like here. For this problem, you have to find the eigenvalues and the eigenvectors and get the general solution, and then plug in t equals 0 and set your solution equal to 2, 2, and solve for your two arbitrary constants. And by the way, a couple of interesting problems here is an upper triangular matrix. The eigenvalues, you can just read them off of the diagonal. You prove it here, but it's it's pretty easy. You just subtract lambda from the diagonal. The determinant is a minus lambda times d minus lambda minus 0. So your determinant is a minus lambda, d minus lambda. It's already factored for you since this product is 0. And so your eigenvalues are a and d. That won't happen if that wasn't 0. So upper triangular is nice because it's easy to find the eigenvalues. Now for a symmetric matrix where these two are equal, you're supposed to show that the eigenvalues will always be real. They can't be complex. For a non-symmetric matrix, they could be complex even though the matrix is real. Okay, to see why they call these two solutions straight line solutions, let's look at the example we did. The matrix is 2, 2, 1, 3, and we saw that one eigenvalue was 4 and the corresponding eigenvector is 1, 1. So it's a scalar multiple of 1, 1, and it doesn't matter what t is, it's still going to be a scalar multiple of 1, 1. So if you start at 2, 2, for example, the straight line, it starts right here, and e to the t increases, because e to the 4t increases, so it goes off to infinity, but it goes off in a straight line. On the other hand, the other eigenvector was minus 2, 1, and that's this point here, and it goes off to infinity also in a straight line because the eigenvalue is positive. If that were e to the minus t, it would go in, but it's always going to be the e to the 4t times 1, 1 is always going to be a multiple of 1, 1 no matter what t is, and e to the t times eigenvector minus 2, 1 is always going to be a multiple of minus 2, 1. So if you start with either one of these solutions by themselves, you go off in a straight line, but you see your general solution, if you start some arbitrary initial point, say, let's just pick one at random here, starting point. Well, that's kind of straight, but not entirely. I'm trying to find one that doesn't look so straight. In general, it's not either one of the straight line solutions. It's a linear combination of the two. So that's not a straight line, although it looks kind of straight. Now notice that all of these problems in chapter 3, 0, 0 is an equilibrium point. That is, if you start at 0, 0, you'll stay there. But what happens if you start near 0, 0? That's one of the things we're going to be investigating quite a bit. So if you start at exactly 0, 0, you stay there. But if you start near it, well, it looks like this is a source because it looks like you get blown away no matter where you start. And that's because both eigenvalues are positive, so the scalar multiple of the first eigenvector is e to the 4t, the scalar multiple of the second eigenvector is e to the t. They both increase with time. So if you start exactly at 0, 0, you stay there, but if you start real close to it, you get blown away. So it looks like it's a source because both eigenvalues are positive.